So, good morning to all of you, welcome to this next lecture. Today we are going to be looking at control of heat integrated distillation columns. Heat integration in distillation systems. First of all, what do we mean by heat integration? Well, specifically heat integration in general means you got a hot stream someplace in the plant, you got a cold stream someplace in the plant. The hot stream needs to be cooled and the and the cold stream needs to be heated up. If the temperature differences are such that they can be brought together, well, so you bring the hot process stream and the cold process stream in contact, not in contact, in energy contact in a heat exchanger, and so the hot process stream cools off and the cold process stream heats up, and this is called heat integration, because now you are not having to use steam, which is expensive, to heat the cold stream, and you are not having to use cooling water to cool the hot stream, cooling water or some other coolant. Okay. So, your utilities consumption goes down. Okay. When we talk of distillation columns, so when you do heat integration, utilities, consumption of utilities, mainly steam and cooling water, this goes down. Okay. So, your steam consumption per kg product produced because of heat integration can reduce significantly. Okay. So, that is the idea behind heat integration. And why do you want heat integration? Because you want to consume less and less energy, because energy is expensive, it is also for economic reasons basically. Okay. When we come to distillation columns, what do we mean by heat integration? Well, heat integration in distillation, the way it is accomplished is you will have a hot vapor stream. You see, you have got a column, you have hot vapor coming up the top, and if this vapor is hot enough, this can be used in the reboiler of some column to create boil up, right, and whatever has condensed is collected in a drum, and then you take it out or reflux it back or whatever you want to do with it. Okay. So, basically what we are saying is the hot vapor is condensed, is used to provide reboil. Hot vapor provides reboil. All right. Now, one of the ways of making sure that the most common way of making sure that the vapor is hot enough is to ensure that the column from which the hot vapor is coming is operated at a high pressure, and this is at a low pressure. So, that you see, the higher the pressure, the higher the boiling temperature, therefore, the vapor will be hot enough and there will be sufficient driving force in this reboiler, so that reboil can be provided to this column. It is already drawn there anyway. Okay. So, typically heat integrated distillation systems will have high pressure columns, low pressure columns. The vapor from the high pressure column will be used to provide reboil in the low pressure column, and there are several common configurations that are prevalent that you will come across, and I will just go through them. So, one of the most common ones is feed split. You split the feed, let us say I split it into two halves, not necessarily half, I split it into two parts. Okay. One part goes to the low pressure column LP, the other part, and let us say the feed is essentially a binary mixture, an AB mixture. Okay. Then the other part goes to a high pressure column. The high pressure column has its own reboiler. So, you got a reboiler and this reboiler is providing the reboil here, and then of course, you got the bottoms that is coming out. Okay. The low pressure column has its own condenser. It's got a small reflux drum. Okay. AB mixture that is going in. The hot vapor from this high pressure column, and let me draw the heat integration scheme in blue, so that it is clear that is how we are well, let us see. So, this has got a, the low pressure column also has a reboiler. Okay, so, the liquid comes down here, there is some reboil going here, and the stream that is the hot stream that is used to reboil the liquid in the low pressure column is this hot vapor. So, this hot vapor is used here. It condenses, and once it has condensed, it is collected in a small drum. Okay. And part of it is withdrawn as distillate. This is also distillate, and part of it is refluxed back into the column. So, you can see that this this unit over here is a reboiler for the low pressure column, and it acts as the condenser for the high pressure column. Okay. Now, if we start looking at degrees of freedom, let us see, you got a valve here, you got a valve here, you got a valve here, you got a valve here. How much steam you are putting in is in your hands, how much bottoms you are drawing off is in your hands, how much is being taken out as distillate from this reflux drum is in your hands, how much is being refluxed back is also in your hands. The feed is what it is. So, let us see, there are two valves. Okay. So, on this T there are 3 streams, of which any 2 will have valves, the third will be dependent on what. Okay. So, let us say I just draw those 2 valves in this way, there is a reason why I am drawing it like this. Okay. Okay. So, is there a valve on this blue line? Well, you can think about it this way, whatever is the reboil that you generate because of steam in the reboiler of the high pressure column, that reboil has to be condensed. So, there is no point providing a valve here, because that will create unnecessary pressure drop. Okay. So, I am not showing a valve on this vapor draw line. Okay. All right. Hot vapor from the top of the high pressure column does not have a valve. to avoid unnecessary pressure drop. All right. So, now let us look at degrees of freedom. Total number of valves 1, 2, 3, 4, 5, 6, 7, 8, 8 because the feet is not counted, total number of valves is 7, not counting the total feed into the system. Okay. How many levels do I have to control? One level here, one level here and one level here. So, 1, 2, 3, 4 to control 4 levels. How many pressures do I have to control? Well, I have to control this pressure. So, one pressure that leaves essentially degrees of freedom is 2. How many things am I free to? Well, I thought the degrees of freedom should come out to be 3. 1, 2, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, of which the feed is not included. So, this guy here should be 8. Now, that makes sense. Okay. So, total number of valves is 8, 4 levels need to be controlled, 1 pressure needs to be controlled. So, that leaves 3 things that the operator can adjust in order to get the kind of separation that he wants. Okay. What are those 3 things? Degrees of freedom is 3. What are those 3 things? Well, operator can, for example, I mean in most conventional systems, operator can set, let us use a different color, maybe the L, maybe this Q, and maybe essentially the split here, how much of the total feed is fed into the first column into the LP column. Given that the total flow is fixed, the remainder goes into the HP column, into the high pressure column. So, the split. So, maybe I do not know what I should call this. Well, let us just say the flow to LP column. So, the operator can get the kind of separation that he wants by adjusting the reflux into the LP column, by adjusting the reboil into the HP column, and by adjusting the split of the feed into the LP and HP columns. Okay. What percentage of the total feed goes into the LP column, what percentage goes into the HP column. Okay. So, degrees of freedom is 3 and I have just explained to you how it should be done. Now, let us just draw a control system for this system. Okay. So, I am going to remove this, also going to remove this, that is fine. Okay. Well, simple things first, pressure control, level control, how do I control the bottoms level? One. Okay. Well, this guy would be under level control, that is for sure. This guy would be under level control here. So, this would be level control. See, I am thinking on the fly, and it is good to think on the fly because that sort of clarifies many things. This would be level control. My question is, how do I control this level? That is the question. Well, let us see. By the way, the distillate will be pure A, this would be A, this would also be A, and so I have taken out, okay, I have taken out whatever has condensed of the vapor, split it into distillate and reflux into the HP column. What about the bottoms from this column? There is no stream showing that. Okay, let us see. So, there has to be a stream here, and that stream, well, maybe I will just show it here. This is the bottom stream from this guy, and it is this bottom stream that is used to control this level. Okay, so in my accounting there are actually 9 valves, 9 independent valves, but then there is one extra level to be controlled. Just a sec, 1, 2, 3, 4, levels are only 4. Well, degrees of freedom I think is 3, but does not matter, let us just keep at it. So, okay, we will worry about degrees of freedom later. So, level control goes this way, this level controller goes this way. So, I have got my level controllers in place. How do I set the reflux in this column? Well, to hold a composition constant, or to hold the purity of, or to hold the amount of impurity in the distillate, that is B, constant. So, I can control either a temperature or a composition, and I will just say composition, but Cc does not necessarily mean composition. You can also control a tray temperature. Okay, this is a tray temperature Tc. How do I adjust the split? Well, notice that the amount of reboil that I get in this LP column is not in my hands. The reboil is what it is. There is vapor that is coming, which is the blue stream, hot vapor. As much heat as it loses in the surface area provided in this reboiler, well, as much heat as it loses, that is the amount of reboil that you, that fixes the amount of reboil that you get. So, the reboil is not in your hands. What is in your hands then is how much you are putting into the LP column. Okay. So, I would like to put only as much such that the amount of A impurity that is coming down the bottoms in this stream. So, this is essentially B with some amount of A. If this amount of A starts to go up, that means my bottoms is getting impure. That means I do not have enough reboil here to split it. Enough reboil is not there. So, the A is leaking down the bottoms of this column. So, therefore, what I should do is, since the reboil is not in my hands, what I should do is reduce the amount of feed that I am putting in. So, what I would say is you do this. So, if the amount of A impurity in this stream right here goes up, then I should reduce the amount of fresh feed that I am putting into the LP column. Okay. By the way, note that pressure in the HP column floats. What do I mean by that? What I mean is, if for whatever reason, because probably the bottoms of the LP column became cooler, so therefore, since more heat got transferred in this reboiler over here, therefore, the condensation rate increased. Because the condensation rate increased, amount of vapor that you are producing is the same, the pressure of this column, for example, goes down a little bit. Similarly, for whatever reason, if the amount of condensation in this reboiler goes down, well, then the pressure here will go up, okay, in the HP column. So, the pressure in the high pressure column will actually float depending on what is going on in the reboiler, which is acting as a condenser and a reboiler, a condenser for the HP column and a reboiler for the LP column, for the low pressure column. Okay, now let us revisit the issue of, okay, how do I set this? Well, this is set so that you have the impurity in the distillate here. If the impurity here, which is small b, if this goes up, well, you need to increase the reflux. So, this is essentially composition control. Okay. You may also use temperature controllers. Since the pressure is controlled in the LP column, Cc can be replaced with Tc, no issues. In the HP column, if you replace, for example, okay, if this is to be a Tc, or this should be actually a Cc, because I am just saying, if you want to say I want to use a temperature controller here, well, notice that the pressure in the high pressure column will float. Since the pressure is floating, you will have to use pressure compensated temperature set point in HP column. Okay. What was the problem that we were looking at? Degrees of freedom. So, now if I look at the degrees of freedom, well, operator can set this set point, level and pressure controllers do not make a difference. He can set 1, 2, 3 and 4. These are the 4 set points that the operator can play with. So, the degrees of freedom is actually 4. Yeah, that is true. If I look at the accounting, 4 levels need to be controlled, 9, 4 and 1. Yeah, so that is okay. So, that is actually 9 minus 5, the degrees of freedom is actually 4. And if I look at what my degrees of freedom are, what those degrees of freedom are, essentially the reflux into the LP column, this guy. How do I say this? If I want to look at the degrees of freedom, well, how much reflux am I putting back into the column? How much reflux am I putting into the HP column? This is also, so reflux in the low pressure column, reflux in the high pressure column, the feed split, the feed going into the low pressure column 1, 2, 3 and finally, the steam going into the high pressure column. So, essentially these are the 4 things that the operator can adjust in order to ensure that all the product streams, which is distillate from LP column, distillate from HP column, bottoms from LP column, bottoms from HP column, all these streams have impurity levels that are acceptable. Okay. All right, I think I've done this feed split business reasonably okay. There is also, maybe we will do the next configuration. Oh, well, 13, 14, yeah, that is fine. All right. So, here is the feed split binary distillation column that I just explained to you, and you would appreciate is the same thing. This is these 1, 2, 3 and there is a 4th one. Where is the 4th one? Yeah, there is this 4th one. These 4 set points is what the operator adjusts to get the kind of split that he wants. Okay. If I go next, let us look at this one and then maybe I will explain it on the notepad. Again, I am having an AB mixture that is coming in. So, there is an AB binary mixture that is coming in. It goes into a low pressure column. The split here is such that part of the A goes up. So, this is A with a little bit of B, but not all of the A. Okay. So, let us say this is 50-50. If this is 50 kilomoles per hour of A, 50 kilomoles per hour of B, the distillate is, let us say, about 20 kilomoles per hour of A with some amount of B, negligible amount of B. Okay. So, then the bottoms is an AB mixture. This is the bottoms from which column? Yeah, from this column. This is an AB mixture. This is sent to a high pressure column, and now this would be 20 has been taken up. This is actually only 30 kilomoles of A per hour and 50 kilomoles. Okay. So, the stream to the HP column has small relatively lesser amount of A. Okay. You have got a reboiler here, you take out the B down the bottoms with some amount of A impurity. The top from the hot vapor from this HP column is essentially all of the A with some amount of B impurity. It is condensed in this reboiler right here. This is where the vapor is condensed, collected in a reflux drum. Part of it is taken out as distillate and the other part is sent back to the HP column as reflux, right. So, this is LHP, this is distillate from HP, this is distillate from LP column, and this is, where is the bottoms from here? This is the bottoms from low pressure column. Okay. So, let us just take a look at it again, and how do I want to take a look at it? Let us just. So, what I have here is I have got a low pressure distillation column which takes in my binary feed. Okay. The low pressure column has got a condenser as before, part of it is refluxed, part of it is taken out as distillate. The bottoms from this column which is this guy is sent to a, let us just say, a high pressure column. The high pressure column has got a reboiler of its own that uses steam to get whatever reboil you want, and of course, part of is withdrawn as bottoms. Feed is an AB mixture. Okay. This is a high pressure column. The hot vapor from the column, and this is where energy integration happens, heat integration happens. This is hot vapor. This is sent this is condensed here, and this hot vapor provides heat to create reboil in the low pressure column. So, the blue stream condenses and that gives you the black stream going as reboil into the low pressure column. The condensate is collected in a reflux drum, part of it is sent as reflux and the other part is withdrawn as let us see, distillate. Okay. So, this is reflux and this is let us see, distillate. If I start drawing independent valves, I hope I do not mess up the degrees of freedom this time. Well, even if we mess up, once we draw the control structure, it will be pretty clear how many things are there in the hands of the operator to get the kind of separation that is desired. We have a valve here. What about a valve here? Yeah, it is a liquid stream. So, yeah, so there will be a valve here, and what would this valve be used for? Probably level control. Okay. Let us see if we have drawn all the valves. Yeah, I think so. If I count the number of valves, 1, 2, excluding the feed valve, 1, 2, 3, so excluding this guy, because the feed is something that is coming from upstream. So, 1, 2, 3, 4, 5, 6, 7, 8. So, there is number of valves is 8. How many levels do I need to control? 1, 2, 3 and 4. 4 level controllers, 1 pressure controller. What is the degrees of freedom? Well, I think it turns out to be 3. Let us just see if this time it is correct. What are those degrees of freedom? The amount of reflux that I am putting into the low pressure column, the amount of reboil that I am putting into the high pressure column, as well as the amount of reflux that I am putting into the what kind of column that I am putting into the high pressure column. Yeah. So, these are the only three things that are there in my hands to get the kind of separation that I want. All right. So, let us draw the control structure, and I think I will use what? I will continue to use this, maybe I will use orange or whatever this time. So, obviously, this is pressure control, this would be level control, this would be level control again, this would be level control. Okay. This level probably will get controlled using the distillate that I am drawing out of here. Now, what is left with me is what I use to get the kind of separation that I desire. So, this guy would be a temperature controller. Well, the pressure, again the pressure in the high pressure column will float, because depending on how much condensation occurs in this guy, depending on how much condensation occurs in this reboiler, the pressure in the high pressure column will float. So, I would say okay, this is Cc. If you want to make it a Tc, you will have to use pressure compensated temperature set points. What is the impurity level in the distillate? Right here, that is what would set this guy. And what is the impurity level here, or trying to set a tray temperature, is what would set this guy. So, the operator is adjusting this set point, this set point, this set point. Through these set points or through these controllers, the reflux in the two columns and the reboil in the HP column gets adjusted to get the kind of separation that you would like. Okay. Degrees of freedom here correctly turns out to be 3. Okay. Over here, and again notice that there are 3 compositions that are being set, 1, 2, 3, and that is it. Okay. Well, if this is an A B mixture, like I described to you earlier, this is A with a little bit of B, A again with a little bit of B, and this is B with a little bit of A. Why was the degrees of freedom 3 here and 4 in the previous case? So, if I go to the previous slide, notice that there are 4 product streams, 1, 2, 3, 4. Degrees of freedom is 4. How many product streams do I have here? 1, 2 and 3. Degrees of freedom is 3. If I have a simple distillation column, I think time is running out, but what the hell, we will just. How many product stream do I have on this distillation column? 1, 2. What is the degrees of freedom of a simple distillation column? 2. Okay. It is very straightforward way of figuring out degrees of freedom. Now, we will look at a ternary mixture, which is to be separated into its pure components A, B and C. So, let us say you got a ternary mixture coming in here, that is A, B, C. Well, one of the most common sequences is called the Petliuk sequence, and I think what I am drawing is the Petliuk sequence. I may be wrong in terms of the nomenclature, it may not be the Petliuk sequence, but there is some name associated with this sequence. And what we do here is, you have a prefractionator. What the prefractionator does is splits ABC into some of the AB going up the top. Well, yeah, so it splits it into AB, BC. So, the light key and the heavy key is B. Okay. So, the prefractionator is at low pressure, okay, and some amount of reboil gets created here. Then there is a main column section which is pretty tall, and this has got a reboiler of its own. I think this has also got a condenser of its own, if I am not wrong. We will see. I have got the PPT right there. Okay. Part of it is refluxed, part of it is taken out. This is okay. So, all right. The bottoms from this stream is actually BC with a little bit of A, let us just say. This bottoms is sent to the main column. Okay. There is no condenser here. What you do here is you take the hot vapor, this is high pressure column, the main column is at high pressure. You take the hot vapor, bring it here, and here it condenses, and after condensation it goes to a reflux drum. Okay, so that is the so this reboiler, this unit here acts as the reboiler for the low pressure column and the condenser for the high pressure column, and part of it is drawn as product, part of it is refluxed back. Suppose this guy will have to have a condenser. Yup, and this condenser won't be too large. And of course, the stream coming in here is essentially AB. So, this is BC, this is also sent to this column and it is sent above this guy, that is because it is lighter than this guy. So, the lighter the feed stream, the further up into the column it should be sent, and you can see that this is AB and this is BC. Somewhere in the middle, if I go down, composition will get purer and purer in B. If I go up, composition will get purer and purer in B, very little C. So, somewhere there is a side draw which is essentially pure B. Okay, and that is about it. So, you have got the reflux, you have got the vapor. Yeah, this is a heat integrated, I think, Petliuk sequence. Okay. Let us count the valves. Feed, of course, I do not count it because the feed is something that is set from an upstream process. 1, 2, 3, 4, 5, 6, 7, 8 and 9. Where the hell? Yeah, of course, that is true. Okay, so if I look at my product streams, there are 3 product streams. This is pure B, like I explained, this is pure C with a little bit of B, and this is pure A with a little bit of B. Okay. That is, if I go up here, if I go in this direction, the tray composition will get richer and richer in A, and so the vapor is nearly pure A, which is condensed and drawn as product, and part of it is of course reflux back. Okay. All right. So, to me it appears, if I look at the number of valves, excluding the feed, there are 9 valves, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice again that since I do not want to take unnecessary pressure drop, there is no valve drawn on this blue line, okay, because that will create unnecessary pressure drop. Let us not call this the PET, this is just a heat integrated ternary sequence. Okay. I do not think this is the Petliuk. Yeah, we will talk about the Petliuk a little later. Okay. So, we were doing degrees of freedom. So, number of valves is 9. How many levels do I need to control? 1, 2, 3, 4. 4 level controls. So, degrees of freedom should be 9 minus 5 4, right. So, degrees of freedom is 4. Let us just see what are those 4 things that can be adjusted to get the kind of separation that we want. Well, of course, this reflux is something that can be adjusted, LLP, all right. LHP is something that can be adjusted, QHP is something adjusted, and something that can also be adjusted is this side draw stream. So, I will just call it side draw from the high pressure column. Okay. So, it appears to me these are the 4 things that can be adjusted to get the kinds of purities that you want, and let us draw the control structure and it will become obvious what I am talking about. So, if I start drawing my level and pressure controllers, well, PC here is in this way. Level control, the most obvious thing to do is this. Level control here, again the most obvious thing to do is this. Level control of this reflux drum, well, the most obvious thing to do is control it using this valve. Okay. Level control here, most obvious thing to do is this. Now, I have put in my 4 level controllers and pressure controller. Now, let us see. Well, the amount of C impurity that is going up the top here, yeah. So, if there is too much C that is going up the top here, I increase the reflux. I can't do much here because the reboil is what it is. The primary impurity in this guy is B. I hold it constant by adjusting. If too much B is leaving in this stream, I increase the reflux to the HP column. If too much B is leaving down the bottoms, I increase the steam, composition control or temperature control. Of course, if I use TC, then because the pressure of the high pressure column floats, I will have to use pressure compensated temperature set points. Okay. I hold the purity of B constant by adjusting the amount that is being drawn off. If the purity is going down, I reduce the draw off. If the purity of B here is going up, I increase the draw off, right. So, what are my degrees of freedom? Well, here goes 1, 2, 3 and 4. 4 compositions are being maintained by adjusting those 4 degrees of freedoms which we had discussed: reflux into the LP column, reflux into the HP column, reboiler duty in the HP column, and the side draw from the HP column, right. So, these 4 things get adjusted to get the kind of impurities in the reflux and or product streams. Okay. All right. So, this is what we have here, the LP column, the HP column, and I will just go through the degrees of freedom. Well, 1, 2, 3 and of course 4, right. So, this is a, of course, it is a ABC feed, and this is what is this, AB, this is BC, this is pure B, this is pure C or nearly pure C, and this is pure A. Okay. Sometimes what happens is you have got a highly exothermic reaction going on, and you know that reaction heat is being removed to generate steam. I will just explain what is going on here. So, here is my reactor, highly exothermic reaction going on here, and what I have is I have let us say water, yeah, it is water circulating in the jacket, and the circulation rate is very high. So, water is circulating in the jacket and the circulation rate is very high, and because this circulation rate is very high, there is hardly any rise in the temperature in the jacket. So, as far as the reactor is concerned, it is seeing a jacket at constant temperature. Because heat gets transferred across the walls, the liquid, the water that goes here, it flashes and generates steam. This is the steam that gets generated. Okay. So, this is of course boiler feed water. Now, because steam is getting generated, the level of the water here will go down, that is made up by putting in more boiler feed water, which is here. Okay. Now, this steam is being used to get some reboil in this distillation column. Okay. So, we have got 5 minutes. Of course, this reboil is not enough to get the kind of split that I want. So, let us say if the amount of reboiler duty that I want is x, let us say the steam from the reactor is giving me maybe 70% or 60% of the total reboiler duty that I want. The remainder 30-40% is coming from this trim reboiler. This is called a trim reboiler. Now, notice depending on what is going on in the reactor, this steam flow rate will fluctuate. So, this steam flow rate is going all over the place, it is fluctuating. Because this is fluctuating, the heat that is transferred from the steam from the reactor will vary, and therefore, the boil up here will vary. Okay. So, now let us say what I am doing is I am controlling a tray temperature by adjusting the reboiler duty of the trim reboiler. How does this work? The steam rate from the reactor fluctuates. So, this is going all over the place. Because of this, the temperature starts to go up or down. As the temperature is going up or down, the steam rate in the trim reboiler goes down or up, so that the temperature is brought back to set point. So, what it essentially means is, because the steam is varying, the steam from the reactor is varying, that creates variability in the temperature. Okay. The temperature must deviate before the trim reboiler can reduce or increase or adjust the reboiler duty to get that deviating temperature back to its set point. How do we overcome this problem? That is a very neat trick. You see, what we are doing here is we are controlling the trim duty. So, if the total duty is x and this x is split into whatever is coming from reactor and whatever is coming from the trim, I am adjusting the Q trim. Now, because Q reactor is varying all over the place, Q trim, the temperature controller tries to vary it all over the place, but the point is my heat duty requirement is x. So, instead of trying to vary this in response to this, how about if I control x itself, that is the total amount of steam, not Q trim, but Q trim plus Q reactor. That is what is being done in this next scheme that is shown here. So, what I have is a flow transmitter. Okay, so it is summing, there is a mistake here. So, this is the flow of the steam from reactor. So, this is flow of steam from reactor. This is the flow of steam from trim cooler or trim reboiler. It is also called an auxiliary reboiler. This trim reboiler, these two streams are, these two flows are summed. So, that is this plus this, this guy plus this guy, this signal is total steam or total boil up, because boil up is nothing but total steam divided by the latent heat of vaporization. So, this total boil up is the signal that goes to this total boil up controller or total Q controller, and the temperature controller is essentially adjusting the set point of the total Q. Instead of adjusting the set point of the trim Q, the temperature controller is now adjusting the set point of the total Q. How does this work? Well, if this steam rate goes all over the place, let us say it is going all over the place, this signal goes all over the place, right? This signal goes all over the place. Now, because this guy is going all over the place, this Q controller, what it does is it actually takes this same signal. This Q controller sees what is the amount of steam. This Q controller, what it does is it sees that the total amount of Q is varying, therefore, it immediately changes the valve position of the trim reboiler, so that the amount of steam here, so that this total stays constant. Now, what happens in this case is, because this guy is changing, because this is changing, the Q controller, total Q controller adjusts this, okay, so that the sum, which is this guy, remains constant. So, there is variability in the steam being generated in the reaction section, because by adjusting the amount of steam in the trim cooler, I can quickly bring the total steam generated back to set point. As far as the temperature controller is seeing, or as far as this distillation column is seeing, the total of amount of boil up remains relatively constant. Now, since the boil up is constant, nothing happens to this temperature. Okay. So, earlier variability in the steam rate from the reactor, from the reaction section, was causing the boil up to vary. Because the boil up was varying, the temperature varied, and in order to bring that temperature back, I adjusted the trim duty. Now, here what is happening is, the boil up from the reactor is varying, the steam from the reactor is varying. However, as the steam from the reactor, for example, goes up, the Q controller, total Q controller reduces the duty or the amount of steam to the trim cooler, to the trim reboiler. Therefore, the boil up from the trim reboiler goes down. So, if steam from reactor is going up, QC will act to reduce steam from the trim reboiler, and therefore, what that does is that this total boil up remains relatively constant. It will not be exactly constant, but it remains relatively constant. Because it is relatively constant, it does not change a lot. Therefore, this temperature does not change. All right. So, in this way, this scheme, in this control scheme, fluctuations in the steam generated from the reaction section does not cause fluctuations in the tray temperature. I would not say does not cause, it causes very little fluctuations in the tray temperature. Okay. So, this is a better scheme than what we were doing here. Okay. In this case, because this guy is varying, the boil up will vary. Because the boil up is varying, the temperature varies. Because temperature varies, then I bring the trim duty down. In this case, because I am trying to hold the total boil up constant, the variability in the total boil up has gone down. If the boil up, if the steam from the reactor is increasing, steam into the trim reboiler will be decreased, and therefore, variability in the boil up will be much reduced. Because the variability in the boil up is much reduced, temperature is relatively constant. Okay. So, in this scheme, the product purity control or the split will be controlled better, more tightly. Okay. That's it for today.